Hey guys, today we're talking about the factor theorem. So recall from yesterday, we learned to factor a polynomial based off of some different patterns. And factors are simply the individual terms that multiply together to give you the polynomial. So today we're going to take a look at the factor theorem and learn what it says about the zeros or the roots of our polynomial. So before we get going here, let's get a few definitions. The zero or the root of a polynomial is the value of x. So it's the value of x such that p of x is equal to 0. In other words, it's where it crosses the x-axis on the graph. So whenever we have a function that's graphed, we're going to look to see where it crosses the x-axis, and those x-intercepts are going to be known as the zeros or the roots or the solutions of that polynomial. Okay, the zero product theorem says if the product is equal to 0, then at least one of the factors is equal to 0. Now this makes sense. Let's just think of numbers like 4 times 2 is equal to 8. But as soon as I multiply something by 0, the product goes to 0. So at least one of the individual factors needs to be equal to 0 if the result of the product is equal to 0. Now here's the factor theorem. It says x minus r is a factor of the polynomial p of x if and only if p of r is equal to 0. In other words, if we take the value of r and substitute it into the function p of x, we should end up at 0. And therefore r is a 0 or a root of the polynomial p of x. All right, let's jump into our examples. Example 1, remember our pizza box problem from the other day. We want to know the volume of the box, and it's shown at the right here. The dimensions are x by 24 minus 2x by 24 minus 2x. So this first form here is known as the factored form, and then we expanded the factored form to get our volume function, 4x cubed minus 96x squared plus 576x. Now the other day in class we graphed this function, and we noted that the graph passes through the origin, increases to a certain point, then comes back down, and then it's going to bounce off that x-axis. So it's going to have a couple of points where it crosses the x-axis, those x-intercepts, and those are going to be the zeros. Now the way we go about finding all the zeros of our volume function here is to take a look at the factored form. So the factored form is going to be the easiest for us. And what we do is we take each one of those individual factors, x, and then 24 minus 2x, and the other one, which is 24 minus 2x. And we are going to take each one of those factors and we are going to set it equal to 0 and solve. So if I take x and I set it equal to 0 and solve, well, I got x by itself already. So what that means is that 0 is a root or a 0 of the polynomial. Next one we're going to do is the 24 minus 2x. We're going to set that factor equal to 0 and solve. So that means I need to add 24 over to the other side. That gives me negative 2x is equal to negative 24. And when I divide both sides by negative 2, I get the value of x to equal 12. So that means 12 is also a 0 or a root of the polynomial. In other words, it's going to be the point where that function crosses or touches the x-axis. Next, our last factor here, 24 minus 2x, it's actually the same as the one above it, so we're not going to work through how to solve that. We're going to end up with the same thing, x is equal to 12. So all zeros of this polynomial are 0, 12, and 12. Now, I'm actually going to list 12 twice. This is going to be known as a double root. We'll talk more about that in the next chapter. All right, let's look at example 2. It says to find all roots by factoring. So in example 2, we're going to look to factor out using our greatest common factor. So if I look across my three terms here, I notice that I can factor out an x squared. When I do that, I'm going to be left with x squared minus x minus 20. Now I have a trinomial inside that set of parentheses, and I know that this is factorable even further. I know that there are factors of negative 20 that add to give me negative 1. So I'm going to break this trinomial down into the factors x minus 5 times x plus 4. And I still have my first factor here, which is x squared. So here are my three factors. Now this is known as factored form. And I'm going to do the same thing I did on the previous problem. I'm going to take each one of the factors and set it equal to 0 and solve for x. So here's my first factor. My second factor is x minus 5 equals 0. And finally, x plus 4 equals 0. So what we're doing here is we're really applying this zero product theorem. All right, and when I solve this, I'm going to take the square root of both sides. Well, the square root of 0 is simply 0. So 0 is known as one of my roots. When I solve this one now, I'm going to bump the 5 over by addition. So that means 5 is another root, or a 0 of my polynomial. And the next one, I'm going to solve for x. Bumping the 4 over by subtraction, I get negative 4. So my three zeros of this polynomial, or my three roots, are 0, 5, and negative 4. So that means if you were to graph this function here, it would cross the x-axis at 0, 5, and negative 4. So you might have something that looks like this, where this is my negative 4, this is my 0, and this is my positive 5. All right, our next example, we want to find the exact zeros of the polynomial function with the given equation. Notice that this is already in factored form. So that's really nice for us. Because it's in factored form, we're just going to take each one of our factors and we're going to set it equal to 0. So I have my 2x plus 3 here is equal to 0 and my x minus 5. That means 5 is going to be one of my roots or my zeros. And the next one, if I subtract over my 3, I have 2x equals negative 3. Then I'm going to have to divide off that 2. So my other 0 occurs at negative 3/2. Now, it would be interesting to take a look at this in Desmos. So if we graph this polynomial, x minus 5 times 2x plus 3, I'm going to pull up another graph here. And we got our two factor forms are, x minus 5 and our 2x plus 3. What you'll notice here is these x-intercepts here are at negative 3/2 or negative 1.5 and positive 5. And that's exactly what we said we would get here for our two roots or our two zeros of this polynomial. Okay, let's move into our next example here. It says to find the roots of this polynomial r of x, and you see here we have this trinomial. It looks like we can factor first. So let's factor out using GCF. If I factor out an x, I'm going to actually factor out a 2x. So I'm going to be left with x squared minus 9x minus 10. Now again, I have this trinomial inside the set of parentheses. I can factor this trinomial further, and that turns into 2x times x minus 10 times x plus 1. All right, so here are my final factored form, and I'm going to take each one of these factors and set it equal to 0 and solve. So I have my x minus 10 equals 0, my x plus 1 equals 0, and when I start to solve these for x, if I divide 0 by 2, I get 0. If I move my 10 over by addition, I get a positive 10. If I move my positive 1 over by subtraction, I get negative 1. So my three zeros for this polynomial, or my three roots, are 0, 10, and negative 1. Now, if you take a look at the graph of this function here, this 2x cubed minus 18x minus 20x, you should see exactly that. My three x-intercepts are negative 1, 0, and positive 10. So hopefully you guys are picking up that all x-intercepts are also zeros of the polynomial, or known as the roots. And that means it is x minus that number will be a factor. These are the factors of the polynomial. Okay, so we're going to use that fact that x minus r is a factor of the polynomial to go back the other way now and to write the equations. So as you can see here, we now have the graph of our polynomial, and we want to write the actual polynomial function that has degree 4 with leading coefficient of 1. And we want to first find the factors by taking a look at the x-intercepts and then multiply them back together. So let's start with the easiest one here. I definitely have an x-intercept of 0. Actually, let's do this. Let's make a column for these. So here we go. Our x-intercepts are 0. And if I count to the left, I think that's a -9 is an x-intercept. And if I count out to the right, I'm going to have 8 and 15. So these are my x-intercepts, 0, -9, 8, and 15. And now my factors go like this. Remember, these are the values of r, and it is x minus r that are the factors. So x minus 0 is just simply x. X minus a -9 is going to be x plus 9. X minus 8 is exactly that, x minus 8, and then finally x minus 15. So these are the 4 factors of this polynomial p of x, which if I write that in factor form, it looks like this. X times x plus 9 times x minus 8 times x minus 15. Now, here's our polynomial. This is written in factored form. In order to get it in fully expanded form, we would distribute the x into the x plus 9 and keep multiplying these polynomials. I'll save that for you to do, and you can show me your expanded form in class tomorrow for a free piece of, let's go on to example 6. All right, in number 6 here, we're going to do the same thing. We want to find the general form of a polynomial function so that it has zeros at -4, 7/2, and 5/3. In other words, these are my roots. That's where it crosses the x-axis. So just like what we did in the previous one, we're going to come up with our factors. Remember, our factors always go x minus the root here. So x minus a -4 turns into x plus 4. And then we have x minus our 7/2. And then x minus 5/3. Now, if you're really good and you want to know like the next step, the ninja trick next step here, whenever you have this 5/3, that 3 here is actually going to come from the number in front of x. And same thing with this 2. So really the proper way of writing this would be x plus 4 times 2x minus 7 times 3x minus 5. And there you go. These are the factored forms. Now, because it says the general form, we also have to allow for some multiple of this polynomial. So what we do is we just put a letter out here as a, and we also have to allow for different powers. So those different powers go like this. You could say to the b power, to the c power, to the d power. And again, those are just variables because we have to allow for there to be more than one root at that number. Okay, example 7, you're on your own. It's just like example 6. See if you can get it. Again, show me your answer tomorrow in class for a second piece of